Great question. So today we are not talking about chips. Rather, we are talking about chiplets. They are delicious, and I know all of you love chiplets, so please help yourself. Good morning, everyone, and warm welcome to all of you here in audience, as well as those who are joining us online. I'm extremely delighted to have this panel on chiplets, and I have with me esteemed panelists. So let me go through a quick round of introduction for all of them. On my left, I have Elad, who is CTO and co-founder of Blue Cheetah Analog Design, which is powering the chiplet revolution with generator-enabled solutions. Elad is an IEEE fellow and an adjunct professor at UC Berkeley, where he has been a full professor until July 2021. Welcome, Elad. Next to him, we have Jaiprakash Balachandran. He goes fondly by JB within ODSA community. He's with Unified Compute Server Group within Cisco, UCS, one of the biggest revenue group in Cisco. And he's leading several R&D initiatives there. He also leads the proof of concept work stream within ODSA. Welcome, JB. Next to him, we have Milind Mittal. He's a fellow at Xilinx, focused on strategic initiatives. He's been instrumental in creation of OpenHBI within ODSA, which you'll hear a lot more today. And in past, he has worked as founding CEO, CTO of networking and storage startups, and he's recipient of more than 140 patents, which is 140 more than I have. And last but not least, we have Sid, who is coming from a processor and interconnect background. Actually, me and Sid go long ways back. We have crossed paths in the industry. He's currently founder and CEO of D-Matrix, which is an AI compute platform company. And before that, he was the SVP GM at Inphi. And I'm going to be your moderator for this panel. I'm Dharmesh Jani. I go by DJ. And I support open ecosystem effort within Meta, formerly Facebook. And I also am one of the co-chairs in OCP Incubation Committee. So with that, we can get started. So the way it will work is each of them have roughly 2.5 minutes to go through their slides. If they exceed that time, feel free to chuck anything you have to get the things moving. And then we'll go through the questions, and I'll encourage all of you also to get to the mic and ask your toughest questions to the panelists. So with that, I give it to Elad.
Great. Thank you, DJ. Thanks, everyone, for being here, and for those watching online. Actually, where is the clicker?
Yeah. Oh, this one.
All right. Thank you. OK. So my name is Elad Alan. As DJ said, I'm the CTO and one of the co-founders of Blue Cheetah. I just wanted to sort of clarify that Blue Cheetah works on many different data-to-die interface standards, but for today, I'll be representing some of the work that myself and others at Blue Cheetah have been doing in the BOW working group specifically. So on that side, I think, since I only have 2.5 minutes, I'll keep this very sort of clean and clear. The main purpose for BOW, the main aim, is to just try and come up with a data-to-die interface that has essentially the broadest applicability and also the lowest overhead associated with it in terms of implementation, specifically at the FHIR layer itself. And so from the get-go, there was an explicit goal made of essentially trying to be agnostic from the particular process or packaging technology. So this is intended to be sort of very portable, both from a process technology and in terms of which specific packages one would use. It is obviously a parallel interface because it is really very much targeted at these low overhead, low energy types of implementations. It is, because we're trying to be somewhat agnostic and broad usage case, there's a fairly wide range of essentially reaches, so anywhere from about 2 to maybe 25 millimeters or so, from anywhere from about 2 to 16 gigabits per second. And I think besides that, let me just remind myself. Yeah, OK. So the other thing I wanted to mention here is that there's been a lot of work and progress made over the last, I'd say really a year and a half in essentially trying to get to quote unquote the final version of the 1.0 spec. And so I'd encourage you all, that's available already, go take a look at that online. There's a whole bunch of details there on obviously example bump maps, electrical specifications and so on and so forth. So the other thing I just wanted to really quickly mention is that there is an effort ongoing now to try and essentially fund and develop a couple of community sort of, let's say, driven test chips. One by Blue Cheetah and one by D-Matrix that Sid, I think, will say some more about in a moment. And I don't want to dive into the details right now, but in both cases, it looks like we'll be able to get, sub 400 femtojoules per bit at 16 gigabits per second. Very, very energy efficient, very competitive solutions look like they'll be coming out of this. So a question that may come up either for yourself or for your management, if you happen to go and try and pitch them, is well, why should I go and participate? There are a number of enticements that I'm listing here, everything ranging from participation in the design reviews, getting actual sort of PCBs with these test chips mounted on them that you can play with them, perhaps even actually releases of behavioral models that you could go and play around with in your own environment, to even perhaps discounts on licensing depending on who you're talking to and how much you contribute. So with that, I think I'll hand it over to JP.
Thank you, Elad. So good morning, everyone. Thank you for coming to this and attending this panel. So let me go to my slide. I think, OK, sorry. Is it Milan next? OK.
Oh, okay.
So OK, let's go to Milan and then I'll continue.
Okay, sure. Sure. So maybe I'll stand up so I don't follow the cues here. Yeah. Okay. So OpenHBI, we started in Feb 2020. And the idea here is to create a standard which is easy to develop for the IP developers already. So very quickly, because it is essentially at some level is compatible with HBM3 bump map and certain aspects of that. So essentially, so as a result of that, we were very quickly able to form the group with participation from key IP vendors, system vendors, and users essentially, and test companies as well. So we have ARM, Cadence, Google, Sci-Fi, Synopsys, Teradyne, and Xilinx currently. It's currently within the umbrella of ODSA. It's a closed work group where you have to be a member of this group. But we are now at a stage where we will be releasing the spec, Rev 1.0. It's basically going through the signature process right now. It will be coming out shortly, within a month or so we expect it to come out. The figure of merits wise, we took a goal of to be very competitive. Focus wise, the focus has been on the fine pitch to start with, and that's the scope of 1.0. But I'll talk about other use cases in the next slide. Okay. So first of all, I want to mention is that being part of ODSA has really allowed us to form this group very quickly. I should have mentioned in the previous slide maybe, is that because it provides an umbrella to even have these closed work groups, right? So all the logistics are there, all the legal framework is there. So we got started very quickly here. And as a result of that, now the 1.0 is coming out. So what's been the learning as in this process we went through is that we wanted to come out with the best figure of merits for the first version, and the focus was fine pitch for that scenario, right? But even with fine pitch, the focus was lower cost substrate, like info technologies and so on. So, but what we realize now is that any standard that wants to establish an ecosystem has to essentially be package agnostic. MCM is broadly utilized. It's not just low cost. So I don't, basically one of the things is to not equate MCM with the low cost, but it's like there are so many OSATs and so many packaging houses that are capable of putting together solutions. So you have to have an MCM solution as well, we realize. Second part is that, of course, bandwidth-wise, the needs are growing. The third part is that when we look for ecosystem creation, we have to go to all the layers of the stack, to the protocol layer. So now, in the next phase, we have multiple threads in progress. One is about enabling for MCM. Second one is higher bandwidth. And the third one is protocol layer specification. And I'll just wrap up with saying that there are several aspects in the spec, and we'll discuss during the panel also, which really facilitate creation of products, which are like, if you just look at the figure of merits from the point of view of the data rates and how much bandwidth per millimeter, they don't really talk to those attributes which are necessary to create a product quality solution. Thanks.
Yeah. So good morning again. So let's get started. So I'm representing the POC workstream, proof of concept workstream in ODSA. I'll be talking about giving an update on our work. So ODSA advocates for open domain-specific accelerators to deal with the Moore's law slowdown issues. And we expect the chips to be composed of multiple domain-specific accelerators in future in the form of chiplets. And successful design of these chiplets requires a good software-hardware partitioning along with the right architecture. So in order to enable this, we at ODSA developed a platform, what we call as a open data accelerator platform, which is essentially a rapid prototyping platform to explore chiplet ideas. So it allows us to explore system architecture, chiplet-based chip architectures before you actually commit to the design, especially when it involves multiple accelerators. You need to explore the complete design space, and that's what it allows you to do that. And what you see in the picture is what we built, and it consists of three basic building blocks, what we call as the pitchlets. The pitchlets are PCB equivalent of a chiplet, and it houses the domain-specific accelerators. And we made sure the connectivity between these pitchlets is very rich. You'll be able to form multiple configurations to explore various architectures. And it supports, in interconnect-wise, it supports both parallel and serial links, and it's protocol agnostic. So you'll be able to prototype very quickly a lot of configurations. And so this is functional. And initially we have three pitchlets. Three companies have contributed to this pitchlets. First is NXP with their ARM Core CPU, multi-core A72 ARM Core CPU. And second one's FPGA from Lattice. And this actually mainly for security and management applications. And third one is a Broadcom 50 gig, 200 gig NIC. Right? With this, you'll be able to compose applications in the network and storage acceleration space. And going forward, we are looking to expand this pitchlet ecosystem in the coming year. And so in terms of key accomplishments, this is actually available today, and thanks to actually multiple partners who worked on this particular project. And and also, we also organized a workshop here. We had a lot of interest attendees. And one thing that came out clear is how do we use this kind of prototyping mechanism to reduce the server TCO. So this is something we'll be focusing on. And identifying that particular use case itself is actually kind of, I think, is a win. And so I don't know if Young is here on this panel here, but he came out with this idea, and we got a lot of support in our workshop. And so what you see is actually the prototype platform. We have demo in the OCP NIC Experience Center. You're welcome to come and visit this. What we are showcasing there is an Amazon S3 in near storage computing capability, near storage acceleration capability in the platform. It's a cool demo. You're welcome to watch. Thank you.
All right, thank you. And what I'm going to do is talk about progress that has been made on the ecosystem side. So clearly that is, a very interesting topic for everyone, right? We really need an ecosystem to come together around these chiplets and really create a marketplace for these chiplets. And a lot of good work has been happening on that front. D-Matrix is a relatively new participant in the ODSA. We are 1.5 years into this. I'm sure there's a lot of folks here in the room that have been participating in this a lot longer. So we keep learning from the folks who are part of this. But we have been very enthused with what has happened over the last 1 year in terms of the accomplishments that have been made on the ecosystem side. And that is what kind of allowed us to embrace building, we are building an AI computing accelerator based on chiplets, and we want to use ODSA interconnects to connect these chiplets with each other. But what we were really enthused by over the last 1 year is, first of all, the participation is just phenomenal. right? There's 70 plus companies and counting, and these are folks from different parts of the value chain. You heard from different folks before this panel that represented their viewpoints. That was fantastic, right? And all these guys have come together to put a spec. I mean, to getting a spec done. And there's two specs. There's OpenHPI. There's BOW. And getting technical feasibility on the specs accomplished so quickly in the last 2 years is phenomenal accomplishment in our opinion. And then now the journey really begins of how do we take this IP and convert it into a system, which is where we are helping as a company. We are building a product that will eventually help system realization. And it's like any journey. It's walk before you run, right? Today the world of chiplets is relatively closed. But what the ODSA is doing is really going to enable opening up that world, right? So you have large companies that have demonstrated the viability of chiplets. There is no debate on that. Now, how do we open it up so that chiplets from various providers can talk to each other? So that's the journey we are on, and we are hoping to be part of that. A lot of good work on the operational cost models. I think you heard a presentation before the panel that talked about the cost models. And really, what drove us to this point is economics. Right, so I think making sure that putting ecosystem of chiplets or solutions with chiplets makes economic sense. There's a lot of focus and rigor that is going into that, and that's really important in our opinion. So we've been very encouraged by that. In terms of the test chip itself, I think what we would really like to help out with here is deliver first IP in the form of silicon into this ecosystem next year. So D-Matrix is on a journey to build this AI computing accelerator with chiplets, shown on the top right there. And what we want to do is connect these chiplets using BOW fast. At D-Matrix, we decided to build this IP ourselves for various reasons. We could not find a 7 nanometer offering in the market that was built for organic substrates and had the target energy number. We are very impressed with the target energy numbers for this interface, 300 femtojoules per bit. So we're going to shoot for that. Right, and we're going to build this. Test silicon is shown, what it looks like is shown at the top left corner there. We're going to put 2 of these chiplets on an organic interposer, different trace lengths connected to each other, and deliver this to the ecosystem in the Q2 2022 timeframe. What we think will be amongst the first, BOW-based silicon that will be available to the ecosystem. So that's really a great achievement in our opinion. So we are very enthused and jazzed about this, really, and playing our small part in getting this IP in the hands of the folks that want to use it. Okay, so with that, I'll turn it over to DJ, and happy to take more questions as part of the panel.
You can take one more. That's fantastic introduction. Thank you very much. So if any of you have any questions, please feel free to ask. But I certainly have a whole bunch of questions. So the very first question I would like to ask is, when you look at die-to-die interface and chiplets, there are 2 popular use cases which people talk about. One is die disaggregation, no surprise there, and then package aggregation. We have heard about this in ODSA. So first question to you, Elad, and then Milind, you can follow up with your response. What do you think, in your opinion, is going to be the first use case driving the BOW interface, which ODSA is working? Is it going to be deployed in die disaggregation, or do you think existing protocols running on PCIe and then board aggregation?
Yeah, so actually, as far as I can tell, they're probably going to approximately happen at the same time. Whether or not we sort of get to an open marketplace that allows you to do the die disaggregation, I think that will take a little bit longer. But I think there are folks that are already now basically trying to do both of those, and in both cases are sort of somewhat motivated by similar things. I think from a sort of performance standpoint, the metric that tends to be slightly different in those 2 cases is usually latency. And the reason for that is just that, that in some senses it's just different starting points of the people that are doing die disaggregation are sort of thinking of taking some on-chip bus and splitting it apart. And so, like a nanosecond matters, right? Whereas if you're coming from the package aggregation world, if you're already going through some, PCIe or other protocol stack, nanoseconds kind of don't matter as much because there's a whole bunch embedded elsewhere. But as I said, I'm kind of aware of folks doing both, and whether or not they'll intercept exactly at the same time, I don't know. But order of magnitude wise, I think they're roughly both happening approximately similarly.
Okay, so in this question, there are a few different aspects to this question, right? So first aspect is that when we talk about disaggregation, within disaggregation, we think there are two use cases. One is that a silicon developer basically wants to disaggregate the solution, SoC for example, or an FPGA, because essentially economics-wise that works out better, right? Or because process technologies you want to use different for different parts of the functionality and so on. So for that is already happening in industry for last 5 years. So that will be essentially OpenHBI, and Xilinx has been doing this its own proprietary solution in past to do that die disaggregation. And I think OpenHBI plays a role now essentially for the same use case. But within disaggregation, there is a second use case, which is the primary use case in the context of the ecosystem creation, which is that you actually, as you disaggregate, you don't want to be doing all the components, all the dies, right? You want to be able to just offload some functionality. For example, it could be SerDes, for example, right? And so on. So so that disaggregation use case, which is essentially third-party chiplets being integrated with your solution, which looks like an integration, but it's really at some level disaggregation, that will take some time. The reason for that is because for that to happen, you have to ecosystem to come together, you have to standardize a lot of other aspects. Form factor, power budget, packaging technology, so on and so forth. So it will be more like either a partner is working closely with you, but technically at some level, that's really still the first use case. On integration side, again, if I can take another minute on this one, is that there are two scenarios. One is that it's really naturally going to happen because process technology is very different, right? For example, ADC, DACs, right? For example, they're very specialized vendors, and today they use XSR or some interface like that. They still do on a PCB, but there are use cases when you go to higher bandwidth, you want to be in package. So there's a compelling reason to do integration when package. So that will happen sooner again, I believe. The second use case of integration where ultimately there's a PCI accelerator and you want to be inside, that will just be driven by the business case, we feel.
Yeah, I had one thing to add. I mean, in my past life, I was in the interconnect and networking world, and DJ, you probably remember that. But there is clearly a use case there where, when you're trying to bring in optics into the solution, there's a clear use case to kind of go with a chiplet-based approach because you have the electrical chiplet, you have the optical chiplet, the two are in a different process node. There's different functionalities, right? And so I think the adoption there has already started. I think we're seeing people who are already going down that path. So this could be, what ODS is doing could be a phenomenal way to kind of, kickstart, further activity in that kind of ecosystem.
So, yeah. Actually, it's interesting. You mentioned about optics, Sid. So that immediately brings a simple question. Is that a die disaggregation or package aggregation use case? Because I can argue on both sides. So thoughts?
I think there's a lot of challenges. I think, first of all, putting optical chiplets together with electrical chiplets. So I think my feeling is, and the jury I think is still out there, but this is an opinion. I think it'll start with die disaggregation, right? And I think people will be so focused on just getting the functionality right, getting the yields right, before worrying about trying to integrate everything into a single package and worrying about things like footprint and whatnot, right? So in my opinion, I think first it'll start with simple die disaggregation, get the functionality right, prove that this can work in a chiplet approach, and then move to kind of more concentrated packaging approaches.
Awesome, thank you. So, JV, you talked about reference design. One of the things I often wonder is, ODS is still working on chiplets. We are not there yet. Is it working? Perfect. Thank you. So the question I have is, how are you thinking about doing a reference design for something which is not here yet?
Great question, DJ. So and at POC, we work with chiplets type of systems, and doesn't exist today. How do we actually do that, right? That's a great question. So when we start, I have to take you back in history, and when we started with ODSA sometime back in 2019. And so the three partners, we want to build a POC. There wasn't any chiplets. The idea of chiplets existing in large companies like Intel. right? There is something not available in the open domain, and there were 3 companies who came together with the FPGA and multi-core ARM CPU and a network processor. And we want to put together, and we want to get a proof of concept to see how things can flow and how architectures evolve, and we want to develop software around it. And there wasn't there wasn't any chiplet interfaces. These are actually really PCB type of interconnects, right? Like PCIe or Ethernet. But we got it started and gave us a kind of head start in our software development architecture. And also we realized as we went further, we realized there are more towards exploring the architectures than committing to it. For instance, if we take one network processor versus another network processor, one FPGA versus another one, right? Or one type of CPU versus another, and what kind of buffer we want to use, what kind of algorithm we can develop. And all these questions we want to answer. The easy way for us to develop is like a modular architecture, that what I showed here in terms of pitchlets, right? So that gave us a kind of foothold into exploring chiplet-based architecture for IC designs. Going forward, can we develop with actual chiplet interfaces? So I think its answer is possible. Something it may not work at the speed of power like 16 gig, what LR and DJAM say they're developing, but we design such that we'll be able to scale down in speed and still be able to work with it. One advantage that with the BOW is actually channel width is small, like 16 lanes, just like a PCI Express. It makes it easier to work with that ecosystem, what we have.
Awesome, thank you. So actually, based on all the discussion we just heard, I think, and I would like to see the reference design become a system in package, and that, in my opinion, is package aggregation.
Yeah.
Right? Because you have set of boards and you're bringing them all into chiplets. And if it
Smaller
happens,
one.
that would be awesome, right?
Yeah.
But anyways, so moving along, I would like to go a little bit deeper into each of these interfaces. I know a bunch of wire is being contributed into OCP as a specification, which is amazing. OpenHBI is also getting contributed into OCP, which is absolutely fantastic because this is one of the 3 charters of ODSA. In fact, it's the #1 charter to create open standard die-to-die interface. So the first question to you, Elad, is can you talk about some figure of merits which were your guiding North Star? And it could be either on the interface performance or first application or first approach for the packaging type. It would be fantastic to hear that from you.
Yeah, so I guess maybe to clarify first, I also joined ODSA probably, specifically in the context of BOW, maybe about a year and a half ago. So, some of what I'm about to say may be deemed revisionist history, but that's okay. So I think basically the design principle for Bo was in some senses not really a figure of merit that's quantitative, but really just essentially saying, hey, can we really build something that is the most common quote unquote form factor, or really most common set of scenarios could be fit under, and that doesn't mean it'll necessarily be the thing that if you took exactly what the spec says and you wanted to do any one specific application, it may not be exactly perfect for that, but at least that's a baseline that would be the widest sort of applicability, and then from there, people may indeed actually do things that are beyond the spec to meet the needs of their own specific application. So I think that was really the main guiding principle. As I touched on, that does imply, obviously, that you need clearly to be able to support the MCMs, because again, that's an important usage scenario that many people are very interested in. But obviously, you can't exclude the advanced packaging technologies, because there's a wide range of things that you really can only address there. It also obviously says that you want to be, largely speaking, as process technology agnostic as you can. Obviously, it's never going to be perfectly so. But there are people that we're aware of that today are doing 65 nanometer, even older generation designs. Obviously, there's people in 5, 3, 7, et cetera nanometer, and so there's obviously a pretty broad dynamic range of process technologies you want to be compatible with there. At the end of the day, obviously, if you do all this and you're not sort of providing technically from the quantitative figure of merits better the solutions that are out there, then you haven't really succeeded. And so clearly, there is an effort and a thought process behind getting to the low energy per bit, keeping latency small, particularly I'd say sort of design simplicity. And I think that was really sort of what was driving a lot of the development there.
So, yeah, go ahead, Milind.
Yeah. So for OpenHBI, so our goal was to basically, get to about, 1.2 terabit per millimeter, looking at the use cases. So really high bandwidth in this generation. And as we look at the options there, right, there has to be certain use cases like that. So we look at the options there. It just seemed like a very natural fit. And also we do IOs for HBM. Right, so we do have a HBM interface as well. So it just seemed like and we did the analysis, like basically a lot of companies have internal different approaches, right? We had few other choices available to us, right? And we really came down to is that in the end, actually, leveraging, a technology that people are familiar with, a lot of IP vendors will have in-house design work underway already, and it comes really, can come to best figure of merits, right, essentially in that class. So that was one goal, to be best, and then that's why we based it on HBM3, essentially be compatible with it, right? So now, as a result of that, one of the goals also was to say that we want to really have this optimized C2C interconnect, and it just naturally came out to that, that it worked out. We explored the path whether that interface, that edge could also be dual purposed, where it can be used as C2C interface, but in certain use cases could also be used to just connect to HBM3 directly, right? So, and that has certain set of use cases that get enabled. So that was second one. Then as we went down this path, then of course, figure of merits wise, of course, picojoule per bit, be very competitive. We are about 0.4. And channel length, basically fine pitch optimized, so on. Then next thing was really just to really focus on what it takes to really create final products, like from the point of view of orientation independence. Like you have a chiplet, you want to be able to put at any edge of the chip then, right? Lane repair capability, right? CCT, which is basically testability interface. So on and so forth, right? There are many attributes around those lines.
So I have an immediate follow-up, actually, based on all the things you're saying. This thought occurred to me that Blue Cheetah is having a bow, and then they're working it in their IPN product. D-Matrix is working bow into their products. Does Xilinx have plans of working OpenHBI into their products, and what kind of roadmap looks like?
Yeah. Well, I think it's fair to basically make that assumption that certainly Xilinx is developing it because it sees applications of it for its own products, right? That's all I can say.
Okay. Yeah. Thank you. Yeah, I wanted to ask that question. Sid, you talked about the ecosystem development, right, which is very critical for getting some of these technologies up and going, especially in open community. When you're vertically integrated, it's a lot easier to manage. So could you give a little bit more color in terms of, based on what you have seen in 1.5 years, how is the health looking? How are the players working together? What do you see as things which ODS has accomplished or doing well? And then perhaps even comment on things where we can have companies do more. I would love to hear your perspective.
Yeah, certainly happy to share my viewpoint or our viewpoint on that, right? So I think what has really gone well is, and I've been part of standards before, IEEE standards where people are trying to put, standards together around, networking interfaces. Putting a standard around any kind of interface is hard, okay? And it requires a lot of, rigor. It requires a lot of coordination across many, many different parties. And that is what I think the ODSA has done just phenomenally well, right? I mean, getting a broad set of participants across the value chain to come together. And I would say and this is the first time such an activity got kickstarted around open chip-to-chip or die-to-die interfaces, to put that group together and to deliver two standards that are very feasible and viable in a span of, I guess it's what, 2-3 years maybe? I don't know, 2.5 years, yeah. I mean, that is just a phenomenal accomplishment. I've seen standards, drag 3+ years in some cases, right? And these are folks who have been working together for 20 years, right? So that I think personally I was very impressed. I think the team at D-Matrix also was very impressed with that. So we decided to kind of go out and embrace this. That's really phenomenal. That's number one. Now that there is a spec and a standard, I think really the journey begins to kind of prove, because now that's where the approaches differ a little bit, because it's not like, this is a widely interoperable standard like Ethernet where companies just naturally go off and build this stuff. Here is where I think there's going to be some help needed, where we kick off a proof point, we kick off the availability of that IP to the general ecosystem. We kick off, people wanting to adopt that. The business models have to come together. And so those kind of things I see will be a few challenges at the group. But, this group has demonstrated that they have overcome, a pretty major challenge in the last 2.5 years. So we're pretty confident that they will overcome this too. But that is where I would see is, kind of the next step is how do we crystallize the IP that has already been specced out? How do we make it available? How do we convince people that it is, economics make sense, and get them to adopt it and create a marketplace with chiplets with that IP?
That's great to hear. And in fact, that gives kudos to all the ODSA folks who are in the audience here and joining us online. It's awesome. All of you have put in work, and you heard it here that is actually very impressive and unprecedented in industry. So thank you all the folks who work day and night and dream about reinventing semiconductor industry in some way. So moving along, JV, you mentioned about software as one of the things which reference design is going to enable. Could you comment on where we are in terms of the software? What is the possibility of that software being available in an open source manner? How is it all going to work so that tomorrow, let's say Blue Cheetah and D-Matrix puts together a bunch of wire test chip, and we are going to use your reference design to test the performance. How is that software going to play and help us quickly do the measurements?
Sure, DJ. So where are we with respect to software? Software is always the hardest part in any project. And we are developing this as software but as a part of ODSA team, but there's still a lot to be done. But let me explain what we have and where are we going with that. So the first is actually we have what we call as a platform software that allows you to test different pitchlets and in automated fashion. And so this will be made available to the community. So we are pretty soon. And so this team has developed a lot of scripts and automation built around that for automated testing, automated performance analysis, right? So that infrastructure software exists today. And also NXP has contributed for their pitchlet, the whole software stack with their Ubuntu OS, which is also they'll be making
That's
it available.
the DiePort software, or which one?
No, this is actually part of their ARM process CPU.
I see. Okay.
And that is actually made available now. And I think soon, once they complete all the discussions, it'll be made available to the OCP, that stack. Today, we are demonstrating S3-like capability. And this is actually a near storage computing capability based on a UDP stack. So one of our partner, Tamin, they developed a UDP stack-based communication with an acceleration mechanism. So that is also will be available, the kind of reference point. And in future, we are looking at more the NVMe-based acceleration. Like there is a new standard coming up called NVMe 4091. And this requires always this kind of computational methods, requires a lot of hardware handoff from the host. And a lot of the standards are in development. So we're actually monitoring it and see we want to use as a prototype to test the ideas. So a lot more to be done. And this software is always the hardest part, especially when you're partitioning something what is existing to right with hardware and software and still in the works. So we have a lot more to do in the community, even software.
Hopefully, we'll be ready for a bunch of wire test chip to be tested in your reference design.
Yeah, absolutely. So Aladdin said, yeah.
Fantastic.
Yeah.
So Milind, you mentioned something about bump mapping in your OpenHBI discussion. So the question I have is, how do you think through within the open standard where you have dies from multiple processes with multiple different type of bump maps, and we are talking open standard interfaces which can span across multiple nodes, etc. So how did you go about thinking of coming up with a scheme which can transcend across all these different combinations? Can you help audience understand that aspect?
Sure, yeah. I'll make a few comments on that. So first thing is, yeah, we do recognize that when you define, so first thing is, in any of these definitions, you have to define what's your unit of interface, like how many signals you have as the basic granularity. Like Bo calls it slice, and we just call it interface unit, right? So once you decide that, then you have to say that you make it easier for implementation. You have to have some number of ground bumps defined and power bumps defined for isolation and power delivery and so on. So once you come up with that, then the next thing really becomes is, how do you organize these bumps? So you have total number of bumps, how do you organize it, right? So there we recognize that you don't want to be very rigid. You don't want to say the pitch is this, exactly this. You want to have a range, right? So like for this, we define 40 micron to 55 micron for this generation. So the final answer to the question that you're asking is basically, so your different process technologies, you may not be aligned properly and may not want to really be strictly aligned, conforming to that. You have to be in the range to be compatible so the IOs can work, but if you're misaligned, right, two parties are, right? So I think the final answer really becomes is, the nice thing about parallel interfaces is that one thing you can give up on is frequency at that point in time. So not all use cases require the highest frequency. So we require that you meet the highest frequency of 8 gigabit, right? If you're within the spec, you should be able to achieve 8 gigabit per second. But I'm just extending it further. Let's say somebody was even not aligned to that. Could it interoperate? Yes, at some lower frequency, you could still interoperate, probably, as long as you conform to certain other attributes, right, of the spec. But yeah, within this range, you should be able to operate at the full speed. Yeah.
Okay, fantastic. And any comments you want to add, Elad, to that in terms of things from Bo perspective?
Yeah, so the particular approach that Bo took, which predates my involvement, so credit goes to the community that came up with it, is basically to say that rather than specifying what the bump map needs to be, there's essentially just a specification on the quote-unquote wire ordering on the interface in between. And so what that basically then says is that, if you've specified the wire ordering, if somebody comes up with a bump map that, happens to work and meets that wire ordering, great. Now, that doesn't guarantee that everyone will come up with bump maps that are easily compatible with each other. And I think, Milind really hit on sort of the key and question that, people will have to face, which is just, okay, practically, maybe in theory you could come up with sort of wiring schemes that would connect, in one arbitrary thing to some other arbitrary thing, but in practice it might become sufficiently painful that, no one would want to go down that particular route. And so there definitely are going to be things where, there'll be sets of things that likely will work very well with each other and sets of things that may not. So the approach that Bo has been taking is to basically put out what we believe are sort of typically recommended bump patterns and sort of stack ups and things of this nature, just to sort of encourage the community to move in a direction and try and maximize that chance for compatibility. But at the same time, if people come up with other things and they magically realize, oh yeah, this is really just better, there's nothing in the standard that stops you from doing otherwise.
Great. Thanks, Elad and Milind. So, based on, we talked about bump map, and now the next logical question is, within the industry, there are over half a dozen parallel interfaces which companies are using. Sid, you mentioned about proprietary interfaces already in existence and chiplet being. So, question to you, Sid, actually. How do you see this play out in the ecosystem? Do you envision, based on, let's say, where D-Matrix is going, a situation where you could have a system in package which consists of combination of multiple interfaces, open, closed? How do you view it? Do you think that European vision is even possible or not possible? Love to hear your thoughts.
That's the billion-dollar question, isn't it? I know, it's a $1 trillion. These days, billions is not much. So anyway, but I think, it's again, as I talked about the journey, right? It's nothing, I think everyone here has an end vision of where you would like to go, right? But that's not going to happen tomorrow or even day after, right? It's going to be a process. The way we see it is for the next 5 years, we see kind of a hybrid, right? Where if we build IP at D-Matrix that is very compelling to somebody, they will open up their world to us, right? And the only way to open up that world is through ODSA, right? So yes, I think we see that initially we might be just ODSA-based chiplets talking to each other for our solution, but the reason we went with chiplets is so that we can facilitate talking to other people. Because it's our claim has never been that we'll solve all the problems at D-Matrix, and I don't think any company can say that they will solve all the problems for the whole world, and that's the whole point of heterogeneous computing and chiplets and so on and so forth. So yes, I think the doors will gradually open. We see in the next 5 years we will be talking to folks that were closed in the past, and then the ideal view is you can marry anybody's compute memory and I/O with anybody else's compute memory and I/O through ODSA.
Awesome. Yeah, go ahead, Ilhad. And others, please chime in as well if you have thoughts.
Yeah, so I just wanted to amplify something that I think Sid was touching on, which is at the end of the day, one of the this is sort of both stated but also implicit. One of the potential advantages of this sort of quote unquote open chiplet interface and markets and things like this is that people can then choose to really specialize in the thing they're actually good at, right? If you exist in a world where everything must be monolithic to be competitive, then unfortunately you have to acquire at least integration expertise in all these different subspaces, right? Whereas if indeed something like chiplets, can exist and people are able to do these things where, you're not the guy that built the SerDes, or you're not the, the gal that, built the compute memory or whatever it is, but, each sort of sub-entity can really focus and specialize and maximize their value add in that subspace. That by itself drives a lot of why you might want these open interfaces, because it just enables people to sort of behave in this way,
right,
rather than being sort of locked into this monolithic entity.
Absolutely agree. By the way, are there any questions from audience? Please feel free to use. Go ahead, Mark.
Am I allowed to ask without a microphone? I'm pretty loud.
Yeah, please go ahead. Yeah, as long as
We'll
it gets
repeat
recorded, we are okay. We want to record your voice, so that's the key.
You guys can repeat it.
Yeah, okay.
So I think Milind mentioned the next layer beyond the PHY. I'm really interested in how the panelists think about what that next logic layer is going to look like. Is it going to look like PCIe compute? Is it going to look like Ethernet? Does it look like both? Does it look like something completely different? Yes. Thank you.
So, yeah, go ahead.
Yeah, so I think the question was, it is clear that people are going to want sort of layers of hierarchy above the PHY just itself. Whether you call it a controller or a link layer or whatever it is, but something along those lines. And the question was sort of, what do we all believe collectively that looks like? Is that a PCIe-like thing? Is that an Ethernet-like thing? Is it something else? And I jokingly answered yes to the question, and that I think all of those will exist. For the same reasons as I think we've all sort of touched on in that, there are a lot of different ways that people want to use chiplets. And so those will ripple up and sort of, be exposed in the types of interfaces that, or the types of controllers that people will build. So I think there's a lot of effort on, let's say the PCIe type of stack that the people are looking at. I'm aware of many folks that are looking more at, hey, I have an on-chip AMBA bus that for all intents and purposes, I just want to disaggregate. And I think the types of designs you end up in both of those are obviously somewhat different. And so I think, people will span that space depending upon what it is that they're really interested in doing. Much like as with everything else, hopefully one or two sort of common things will emerge so that, it just becomes easier for people to use these things. But at the end of the day, I think that's still very much, there's a lot of work still to be done there.
And are those things we should be defining in OCP along with the PHYs?
Yeah, no, absolutely. I mean, I believe there are groups, working very much in that direction. I personally am not. I don't know yet if sort of the types of bifurcations that I expect will happen have been sort of explicitly decided as this is okay, and we'll just develop multiple versions of these things or not. As far as I understand, I think all that's still somewhat shaking out. But there may be others here that could comment further with better direct knowledge than me.
I'm super interested in Milind's thoughts about this as well.
Yeah, sure. So my thought is that both will exist, as was mentioned. Is the audio okay? Yeah. So, but I think that the area of innovation really is going to be is really non-PCIe and CXL. I mean, people will have standard ways of carrying them. That's fine, right? But the question will be when even if you're carrying, let's say, CXL or PCIe, right? Then when you are in a in-package scenario, you don't want to necessarily go through the whole PCI stack, right? I mean, you want to come up with, because attributes are very different. I mean, your like, for example, for OpenHPI today at Rev 1.0, the bit error ratio is 10 to the minus 25, right? So it's basically a reliable link. You still want to have some integrity checks, right? So with that construction, I think the stack has to be built up, and not to think traditional way. I mean, that's one of the things to see it is that, I have a PHY, I have a logical PHY, I have a data link layer, and I have that, right, so on. But really come up with the optimized partitioning, right? And ultimately, it will top level will come down to is this, that there are some protocols where the packetization is already defined, like PCIe and CXL and so on, right? There are areas where work is in progress, like AMBA, right, for example, right? And essentially, so that will come down to is essentially standardization around those types of items. Like you packetize everything appropriately, then you have adaptation layer to map to your definition of the slice or logical interface. So I see an adaptation layer in the middle of the total packetization layer and your PHY stack.
Can I keep asking questions? Just to Sid, you shared with us that you're implementing something today. What are your thoughts on logic layers? Are you planning on implementing something? Can you share what that is, or can you not?
And I'm glad you brought this up. It's a very, very important topic, right? In fact, when DJ asked me the question, like what's areas we could actually, do better, this is certainly one of those, right? In terms of participation. I think there's work to be done, right, to be honest. It's unclear. I mean, given our timeline, it is unclear how we will proceed, at least on this first revision product. We'll have to just wait and see what progress the ODSA will have made in the next 6 to 9 months. I believe NXP has put out something to help the kickstart that process, right? But I mean that needs to be vetted out. There's a lot more work that needs to be done around it, and there's the rigor that went into the PHY spec has not yet gone into the link layer spec, right? And that is something that we'll have to just wait and see how it plays out over the next 1 year.
Great. Yeah. Thanks, guys.
Okay. Great. Thank you so much.
So I think we are out of time. So we are going to stop here. One just final question. I know we all love chiplets. So would you like to have some? So with that, thank you all for joining, and thank you, panelists, for sharing your insights.